Hello, Earth Science students. Just wanted to say congratulations on making it through the hydrogen fusion section of class today. It's quite a tricky piece of chemistry that you were learning in class today, so I commend you on your efforts there. This is a little bit of a review of that, connecting it to the activity we did in class, and then to where we're going to go with all that information. So just a quick recap here. We started off in the sun, and in the sun we have a lot of hydrogen. And when that hydrogen collides, pow, we not only release some energy, but we also create a special hydrogen that has a neutron. And then that special hydrogen with the neutron then smacks into a regular hydrogen, and that's where we get this version of helium. That's not quite complete because then that version of helium smacks into another version of that helium, and we release again some energy as well as hydrogen, and we end up with helium. So this is a process that can cycle throughout itself, so recycle, and then we basically are forming helium from hydrogen along with vast amounts of energy, and that's what we feel on Earth as solar radiation, or heat and light. So that was pretty cool. So then we took that concept and we did a little experiment about the heating and cooling of different materials. So yes, the solar radiation comes down because of that fusion process, but then once it hits Earth, there's different formations on the Earth itself, as well as different aspects of the atmosphere that affect that radiation and what it does to the Earth. So we looked at salt water and soil and what would happen when we heated up with a heat lamp above, kind of in replication of the sun. What would happen when we heated up soil, salts, and water. And then again, what happens when you turn that lamp off and the system cools. So this is a graph of the whole experiment. Right here at minute 12, right with this peak triangle here, that's when I turned off the light and we started the cooling process. So you can kind of see it made a really, at least for the soil there, made a really nice rise and then fall. We will be discussing this in class tomorrow. You should be familiar with this graph by tomorrow and understand that the soil really changed the most in absorbing and cooling, whereas the water and salt, they maintained a pretty steady level. Yes, they did rise a little bit, but it wasn't as drastic as the soil. Alright, so then with this, we're going to start thinking about the atmosphere. So as the sunlight, as the solar radiation comes down, we want to think about what's happening in the atmosphere and on Earth's surface. This picture shows a little bit about the solar radiation getting dispersed or scattered when it hits clouds, when it hits stuff in the air, as Dr. Shaw called them, aerosols. That was one of the things that Dr. Shaw was measuring at his weather station. And then down here on the Earth's surface we have water and land. So this is kind of a brief overview of why we did the experiment, because we want to look at how the different materials that make up the Earth could affect absorption and emission of heat and light. One of the things that's really important with the idea of absorbing and radiating heat is convection and conduction, and that's going to be really important in our discussions on weather. Take a second and look at this system here. This is a replication of things that can happen in the atmosphere as well as in the interface between the Earth's crust and the atmosphere. So conduction, as you can see here, is pretty much the direct transfer of heat from a heat source to something that's taking in the heat or absorbing the heat, like this pan. Whereas in convection, we have this pot of water, and the heat source is heating the water at the bottom of the pot here, and then that heated water mixes with the cooler water above it and creates these circles, basically, these paths of um, hot and cold temperatured water flowing. And that's called convection. That's when you have movement because of a difference in heat. So then let's think about that in relation to the Earth. So we know because of the shape of the Earth, the equators receive a lot more heat and direct radiation than the poles. Just because if the sun is here, this is closer to the sun than this. So what we're looking at here is a simplified version of the convection concept. So when the solar radiation hits the equator, that creates warm air in that area. And then we know warm air rises, and so we get this uplift of warm air near the equator. And then it could either go north or it can go south. Either direction, as that warm air moves, it meets cold air. And then this cold air is dense, it's heavy, and so then it sinks. And so as it sinks, we then get it meeting up with the warm air again, and the warm air rises, and then you get this circuit created. And you can see that happening on basically 4 quadrants of the Earth. So keep in mind that this is a simplified version. In actuality, we've got something more like this happening, where we have these cells, these belts of different convection cells around the Earth due to warm air rising and colder air sinking, warmer air rising, colder air sinking. And this plays a huge part with our winds. So I'll leave you with that at the moment to think about. For class tomorrow, we'll be taking a look at what convection means and how that affects the winds in relation to solar radiation, the atmosphere, and Earth crust absorbing and releasing that solar radiation. So it's all connected. And please, as always, let me know if you have any questions. Email me, call me, come knocking on my door. Have a good night.